Hey everyone, Sean here for Lambda School, and in this objective video we're going to be talking about something called processes, with the overall objective being to basically learn how computers actually execute programs. And this idea of a process is a central abstraction that comes around when computers actually execute programs. In other words, we're basically going to talk about what happens under the hood in your machine when you, for example, execute some Python file in the Python REPL or execute some C executable that you compiled from some C code. So what is actually happening when you give the command to execute the logic in those files. And so to first start off and trying to answer this question, we need to talk a little bit about what does a computer need to actually execute a program. Well, first off, a computer is going to need a CPU, a central processing unit. More specifically, whenever a program is executing, the CPU basically needs to be executing the logic that's laid out in that program. And so again, a processing unit is of course going to be essential to actually executing the logic. And the other important thing that we need in order to execute a program is some memory. Because when we're running a program, essentially when we're running a program that is manipulating some state, typically within the program itself, right? Because perhaps we're updating some values, updating some data structures, or just some other sorts of data, et cetera, and we need some memory in order to hold on to that state as the CPU is actually transforming that data and updating values and things like that. So again, we need a processing unit that actually makes those updates and makes the changes, and then we need some memory in order to actually persist those changes. And so these are the two things that are pretty much essential to executing a program. So let's talk about the second point a bit. So when we said that a program needs some memory in order to execute, let's talk a little bit about how is a running program actually represented in memory. So here we have this diagram. You can imagine that this represents some segment of RAM, of working memory. So and you'll see at the bottom it says a low address, and at the end it's a high address. So imagine these are the boundaries in which this is the memory that is allocated to some program, to some process. And here again, when I mean process, I just mean a process is a program that is executing. All right. So we have this segment in memory dedicated to some arbitrary process that we're running on our machine. And so there's a couple of things here that we need that needs to be kept track of in this segment of memory. So starting at the bottom, starting from the low address, you see it says text. And basically this text is the actual code of the program. So whatever is the actual instructions that specify the logic of the program, that of course needs to get stored as part of the executing program, as part of the process, so that the CPU can read from that and actually execute those instructions. So that's what text is here in this case, along with any sort of initialized data that comes a part of initializing that process from the text. There's another segment for uninitialized data, and at the other end we see this at the high address. It says command line arguments and environment variables. So those might be any sorts of inputs that we passed into our executable program, into our Python file or to our C executable, whatever. Again, programs are able to take in inputs, and so those inputs might be stored in this segment of memory dedicated to this process. And then in the middle, we see these two parts, stack and heap. So what are these? So starting with the stack, and I want to say, don't confuse this with the stack data structure. They share the same name, but they don't confuse them to be the same thing. Although Well, I guess I should say the stack here in this case is indeed a stack data structure, but let's talk a little bit more specifically on what it's actually storing. So the stack here is indeed a stack data structure, but the importance of it and what it stores is it stores data that belongs to certain scopes in the program that you're executing, right? So let's imagine in some code in some program that you're executing, there's probably a number of functions. Let's assume there's a number of functions in this program that you're executing. And so when each of those functions maybe gets called by the program, by the process itself, every time a function is called, there's going to be some associated data that belongs to that particular function scope. And so that data is all local to that function scope. And so that data that is local to a particular scope in a program is actually stored in the stack area of the allocated memory. So again, that's more for like local data that is not meant to be persisted past a certain scope. Okay, so again, you can think of that as data that's local data, again, that is part of a particular scope. And then on the other end, we have a heap, which in this case is, again, don't confuse it with a heap data structure. In this case, it probably isn't even implemented as an actual heap data structure. It's just called a heap. And in this case, the heap is the area in memory dedicated to persisting long-term data. The rule of thumb is this. Anytime you actually call malloc, for example, so if we say we're in some C program and you call malloc in order to allocate some memory, that memory is all going to be put inside of this heap segment of this memory, of this allocated memory, right? So in contrast to data that goes in the stack, which again might be like variable values local to a scope or a static array in C, again, those are all local to a certain scope, right? And so all that data goes in the stack region, whereas in contrast, when we allocate some data or some memory using malloc, that memory persists past scopes. And so in that case, that longer lived memory is put inside of this heap segment. So again, the rule of thumb is local data that is local to a particular scope goes in the stack. Any other data, more longer lived data, or data that persists past scope level, goes inside of the heap. And again, another rule of thumb is any data you malloc, you know that that's going to go in the heap. So next up, let's talk a bit about some of the properties of processes. And the first kind of important property that we're going to talk about is the fact that processes are all isolated by default. So what does that mean? Basically, that means that processes are not by default able to communicate or talk to any other process. So if you have, two processes running on your machine at a time, by default, they're not able to communicate. They're not even aware of each other, right? And this is a consequence of the fact that every process has its own dedicated chunk of memory allocated to it in RAM, right? And so because each process has its own dedicated memory space, address space, these don't cross boundaries. And so no process is ever aware of any other process, again, due to the fact that their address spaces never cross over into each other. And so this is why processes are by default isolated. I say by default because there are ways to get around this. It's just that operating system designers and developers decided that by default we're not going to enable this functionality. Again, it is certainly possible. It's just something that needs to be set up by a developer who wants to utilize this sort of functionality. And so one thing you can try is if you're, for example, on a Mac, you can type in the command top into a terminal, and on Windows, I believe the analogous command is task list. So if you type either of those commands into the appropriate, or if you type in the appropriate command into a terminal for your operating system, you should pull up, basically this is the process list. So we see a screenshot here of when I ran the top command on my terminal. And when you do that, it pulls up every single process that is running on my machine, right? And we'll see, you can see the names of the commands. You can see PID, which stands for process ID. So every single process has an ID associated with it. And then we can see these other useful statistics, such as CPU percentage. So how resource intensive, I should say, that particular process is. And so, for example, we can see Slack is taking out 15.5%, which is rather significant because Slack is a resource intensive application. And then we can see a whole bunch of other stuff as well. We can also see the amount of memory that it's using up, as well as a port number and things like that. So again, this is the process list, and this is a list of all the processes on your machine that the operating system keeps track of. So when you type in top, the operating system just spits back at you every single process that's on the list. And indeed, this isn't all of it, right? You can keep scrolling down and to see more. So there's way more than just the number of processes listed here. But suffice to say that there are a lot of processes running on your machine probably at any one point in time. You can see at the very top left corner of the screenshot here is that I have 225 processes total running on my machine, with 2 of them actually running and then a whole bunch more sleeping. And sleeping here means that they're not actively running, they're in the background, and perhaps they're just persisting because, you know, they don't actually need to be awake right now, or whatever task it is that they're supposed to be executing doesn't need to be executed right at this moment. So really I only have 2 running right now. Okay, so moving on, let's actually answer the question now of what happens when we run one of these, when we execute some of these commands, when we execute some Python file or we execute some C executable. So far we've talked about kind of background of kind of what processes are, how they're represented, how the operating system sees them, and things like that. We haven't actually answered the question yet of what actually happens when we execute the command. So the steps for actually initializing a process, and a process is initialized whenever we run some executable, because when we run an executable, we basically need to initialize a new process that represents that that program that we just specified that we wanted to execute. So the first thing that's going to happen is some segment of working memory needs to be allocated for the program that we just said we want executed, right? Basically, that segment of working memory is called the process's address space. So we need to go and initialize, or we need to allocate memory for that process's address space. Once that memory is allocated, then we can store things like the text and any other initialized data, the stuff that we saw when we were looking at that diagram, that can all be put into the address space for the process that we just initialized. Next up, we would have to go and also add an entry to the operating system's process list, right? So that long list of processes that we just looked at, we'd have to add a new entry to that list because we just started another process. And so that list needs to keep track of every single process that is running on your machine at any point in time. And so we're going to have to add a new entry to it so that the operating system is aware of that process, because the operating system, again, keeps track of all running processes. Then lastly, the newly initialized process will now have to be scheduled to be run by the operating system's scheduling algorithm. To this last point, let's talk really quickly about scheduling. We're not going to go into this in a whole lot of depth in this particular video, but it does warrant a quick mention. Scheduling in this case, or one of the big responsibilities of the operating system, is that we saw the entire list of processes when I ran the top command in that screenshot. Basically, there's a whole bunch of, again, we saw there were 225 available processes that might be, vying for CPU time, right? Because processes can only get run when they have some time allocated on a CPU. And we saw that there are 225 processes, but on my machine, I only have 4 cores, which means that at any point in time, only 4 processes can be running at any point in time. Each CPU can be executing the instructions from one process at a time, right? So in that case, again, that means that we can only have truly four parallel processes going on or being executed at a point in time. And so the problem of scheduling revolves around, okay, as the operating system or the operating system scheduler algorithm, how does that figure out how to actually efficiently take all of these 225 processes and divvy them up in such a way such that all of those processes are fairly getting CPU time. And then that has to deal with a whole bunch of finicky details such as how long do we run each process on the CPU, for example, right? Because when we're actually, again, in this illustration here, if we have an example process list, basically the idea is that we need to be constantly switching through all of these processes, swapping them in and out of the CPU. So basically the idea is we'll take some process, give that to the CPU will execute it for some amount of time. Once it's done that, it's going to get put back in the process list, and the next process is going to come up and run on the CPU for some length of time. And so this process of swapping through all of the available processes, that's called context switching, because the CPU is context switching between a whole bunch of processes all the time. And so this is kind of how we achieve this illusion of true multitasking on modern computers. So basically the point being is that your computer is not truly multitasking many different programs. It's constantly switching through a bunch of them so quickly that it seems like it is actually multitasking, or it is actually performing multiple tasks all at once, when really this isn't the case. This is all kind of just an illusion. And so operating system scheduling algorithms have to figure out, the order in which processes need to get allocated to the CPU, as well as how long does the CPU run each process for. And then there's a lot of other considerations as well that we're not going to talk about right now, because this video is not actually about scheduling. Anyways, so that's all we're going to say on scheduling for now in this video. Let's move on to the next point, and that is that not all processes are created equal. And what I mean by that is that it turns out that the operating system itself is actually nothing more than a conglomeration of a bunch of processes. But the only difference in this case being that the operating system, the processes that make up the operating system, you can consider them as quote-unquote privileged processes. Privileged here meaning that they are allowed to perform privileged operations. So it turns out there's this notion of all the processes that are running on your machine, there's this notion of privileged versus non-privileged processes. And as you can probably imagine, most processes are going to be non-privileged. Any sort of program that you write the code for yourself and then execute on a machine, that's going to be a non-privileged process by default. With pretty much the main exception to this rule that a process is non-privileged are processes that are part of the operating system. So for example, the scheduler algorithm that we talked about a little bit earlier, that's another process, but that one is the scheduler algorithm, the scheduler process is a privileged process. And there's other processes as well. For example, there's a process that's part of the operating system that is dedicated to managing memory resources, for example. And so that process would also be considered privileged. This is a good segue then to enumerate, what are considered privileged operations. So what are the operations that only privileged processes can execute, or I should say, what are operations or what are privileged operations that non-privileged processes actually are not able to do by default. Some of these include creating new processes, destroying existing processes, allocating memory, and accessing hardware functionality. Of course, there's more than that. What we just listed here, but these are some of the most important ones. Okay. But you might think, wait a second, how does that work? Because we've certainly written programs in C that allocated memory because we have used the malloc function. And we know that malloc actually allocates memory for us. But then that means that it seems like there's a contradiction here, right? Because we just said that allocating memory is a privileged operation, except we were just able to allocate memory from a non-privileged process, because again, any process that we write ourselves is by default a non-privileged process. And so shouldn't that mean that it shouldn't be able to allocate memory? So I'm going to leave you guys on that note, and we're going to essentially answer that question in the next video of how can non-privileged processes actually perform privileged operations? Because, well, it turns out if non-privileged processes were not able to perform these privileged operations, they wouldn't actually be very useful at all.